programme, we're going to be looking at a mathematical model of a particular kind of random process, a battle. The mathematical theory of conflict owes much to the English motor engineer Frederick Lanchester, an underrated genius. In 1916, when conflict was very much on people's minds in Europe, he published the book Aircraft in Warfare, The Dawn of the Fourth Arm, in which he looked at various aspects of aerial conflict. He proposed for the first time the tactical use of aircraft on the battlefield and showed what principles determined their effective use. We could have used other examples than that World War I dogfight you saw, such as a naval battle, a medieval tournament, or even two groups of beetles competing for the same resources. In these conflicts, each group is losing numbers randomly, and it's a matter of chance whether this force or that wins the battle, whether this beetle or that survives, whether victory goes to Sir Gawain or Sir Lancelot. To support his mathematical argument, Lanchester referred back to a past age, the age of Nelson. The date, 9th of October 1805. The Battle of Trafalgar was about to begin. Intelligence reports indicated that Admiral Nelson's fleet of 40 ships would have to face 46 of the combined fleet of French and Spanish warships. The British fleet on the left is outnumbered. How great a disadvantage could this turn out to be? What I'm going to do is to use a computer to see what might happen when a fleet of size 40 actually engages a fleet of size 46. The simulation is based on modelling assumptions that we'll be developing during the programme. In this particular realisation of the battle, the British fleet has been annihilated, with 27 French warships surviving from the original 46. Well, before the programme, we ran 10,000 simulations like that one, though we didn't bother drawing out the pictures each time. The French fleet won almost 9,000 of the battles, and although their numerical advantage was only 15%, most of the time they won with over half their fleet surviving. That's a remarkable result. Once the mathematical model is developed, we'll use it to investigate whether Nelson can do anything to avoid such a miserable defeat. So what features should the model take into account? Quite evidently, in any military engagement, the larger force is going to possess something of an advantage. But there's something else which we need to take account of as well. And that's any difference there might be in the combat effectiveness of either force. That's a matter of training, weapon design, target vulnerability, and so on. Here, we've got one unfortunate individual facing 10. But actually, things aren't as bad as they look, because the 10 units on the right haven't got any weapons. What we've done is to assume that the single fighter on the left is killing the opposition at random, according to a Poisson process. And the rate of the process is a parameter of the model. It's the average rate at which the single fighter can kill opponents. It's called the kill rate. Now we'll run a second battle, where the single fighter has been joined by 5 others, identically armed. They're still facing 10 unarmed opposition. The battle is over much more rapidly. If each armed fighter can kill the opposition according to a Poisson process at the same average rate, then the overall kill rate realized by the force of 6 will be 6 times that of each individual. Well, it's in the nature of battle that usually both forces are armed, though not necessarily with the same weapons. In general, we call the forces blue and red. The blue force is initially of size B0 and will assume that each member of it is capable of achieving an average kill rate beta. We use these angle brackets to designate the force. The opposing red force is initially of size R0, and the average kill rate of individual members of the red force will denote by rho. Let's suppose that the 6 blue units can all kill opposition at an average rate of 2 per minute, much more than the 10 red units, who with a kill rate of 0.8 all take more than a minute on average to achieve a kill. So we've got one force facing another composed of a larger number of less capable units. What's going to happen? We'll watch the progress of the battle using a different schematic representation. The size of the blue force is measured along the horizontal axis, and the red force is counted up the vertical axis. We're starting with a blue force of size 6 and a red force of size 10. The first casualty was a blue casualty, and we've moved a distance 1 to the left, parallel to the blue axis. The blue force is now of size 5, the red force is still 10. We call the coordinate 5, 10 the battle state. Now, blue has killed a red. We're at the battle state 5, 9. What's going to happen next? Will the next casualty be blue, or will it be red? Well, remember that each blue unit is killing red according to a Poisson process. At this battle state, the blue force can kill red opponents at 5 times the rate of individual blue units. The red force can kill blue at 9 times the rate of individual red units. But that's just at the specific battle state 5, 9. Let's look at a general battle state XY. X blue units and Y red. From the battle state XY, we can move to one of 2 different states. There might be a red death, which takes us from Y to Y minus 1. That's a blue kill, and would happen as the first event in a Poisson process at rate beta x. On the other hand, there might be a blue death, taking us from x to x minus 1. That's a red kill, and these happen at rate rho times y. The probabilities of the 2 possible events are proportional to the rates. One or other event has got to happen, and so these are the probabilities. We can now return to the battle state 5, 9 and calculate the chances for the next death. A red death would take us to 5, 8, and the rate for that is beta times x. 2.0 times 5, that's 10. A blue death takes us to 4, 9, and rho y is 0.8 times 9, 7.2. Dividing by the sum, 17.2, we get these probabilities. From this battle state, a red death is more likely. The different probabilities for all the battle states are loaded into the model, which can then be run to the conclusion of the battle. This happens when the battle state reaches one of the axes. A process like this is called a random walk, and in this representation we're only interested in the battle states, not the time it takes to get to them. Red eventually won this battle with 8 survivors. Let's try another one. Blue won that one with 2 survivors. We can run as many simulations of the same battle as we like. As long as there aren't too many units involved in the battle, then the probability of winning and the distribution of the number of survivors can be calculated by hand. Let's take a look at some runs of the 40 versus 46 battle, the numbers that intelligence reports had led Nelson to expect. This was the battle which Lanchester analysed mathematically. He assumed that the kill rates of individual ships in both fleets were equal to each other, so we'll set them both equal to 1. As before, we're calling the British fleet blue and the French fleet red. The initial battle state is the coordinate 40-46. We'll run 5 battles, and you'll see the results coming up on the left-hand side of the screen. Here, red won with 26 surviving ships. And there's just one blue win with 9 survivors. You can see that although the French start with a numbers advantage of just 15%, they practically always seem to win. In fact, the probability that they do win is about 0.86. Things don't look good for Admiral Nelson. What Lanchester did was this. He developed a deterministic version of the battle model, that is, one which ignores completely the element of chance. Such a model is used to trace the average course of the battle. The kill rates are assumed to operate steadily and continuously, and the battle progresses as a smooth process of attrition, rather than as a jerky sequence of casualties. Again, it's over when the curve hits one of the axes. The mathematics goes like this. Starting with initial force sizes B0 and R0, we'll denote the force sizes at some time t by B and R. We know that the average rate at which the blue force is suffering casualties is rho times R, while the rate at which the red force suffers casualties is beta times B. The rates are operating steadily and continuously, and the deterministic version of the model consists of 2 simultaneous differential equations. The minus sign shows that force sizes are decreasing. Finding the solution of the equations isn't difficult, and the technique's given in the text. The solution involves a constant, and this constant, which might be positive or negative, remains the same throughout the entire course of the battle. That means it's equal to what it was at the beginning, when B was B0 and R was R0. Now, we can use this relationship to tell us when 2 forces are matched. That is, when neither side emerges victorious from the battle, but instead there's mutual annihilation, with B equal to 0 and R equal to 0 together. If we put these values into the equation, we get 0 equals beta times B0 squared minus rho times R0 squared. And so, that's the condition for matched forces. The individual kill rate multiplied by the square of the initial force size must be the same for each force. So we've derived Lanchester's square law. The fighting strength of a force may be broadly defined as the square of its size, multiplied by the kill rate of its individual units. Now, when one force is stronger than the other, we know that the difference in strengths remains constant throughout the course of the battle. At the end of the battle, this difference will therefore be the strength of the winning side. That's because the losing side has no survivors, and therefore 0 strength. From this, we can easily calculate the number of survivors. As an example, we'll take the case of 30 blue against 50 red, where the outnumbered units are actually more effective. The initial strength of the blue force is 1,080, rather less than that of the red, which is 1,500. Red will win the battle with a surviving strength which is the difference 1500 minus 1080. From this, we can calculate the number of red survivors. The solution is fractional, but then we're talking about the average battle. In any case, with R equal to 26 or 27, red has survived with just over half the original force intact. Lanchester was particularly pleased with what he called his n-squared law of conflict. In his later years, in a letter to the journal Engineering in 1939, he claimed, "The most important thing I did was discover the fundamental law that lies at the base of many problems in strategy and tactics, what I term the n-squared law." The importance of his law to military strategists is that it emphasizes the principle of force concentration in a battle. At the time of its publication, an admiral of the fleet wrote, "The n-squared law is the mathematical statement of the facts of concentration. I only wish it was appreciated in the highest quarters. There is still an idea current in the service that a ship will always put its opposite number out of action even though sunk itself. That's to say, if 6 ships against 4, only 2 of the greater force will survive, a fallacy which should be corrected on every occasion." Field Marshal Slim often used to quote the military dictum, "The more you use, the fewer you lose," and this too is supported by the square law. As an aid to the development of maxims and principles of battle, the deterministic model can be very useful. Let's go back to Admiral Nelson and the problem of the enemy fleet and see if we can use it there. The British fleet of size 40 is to engage the combined French and Spanish fleets of size 46. We'll use the square law to gauge their fighting strength. We don't know about the relative combat effectiveness. We'll assume throughout that they're the same, and for simplicity, equal to 1. The strength of the British fleet is 40 squared, 1600, which makes the French fleet, at 2116, much stronger. The difference is 516. Take the square root of that, and the square law forecasts a French victory with nearly 23 surviving warships. That is, with almost exactly half the fleet surviving. There is something which Nelson could do, if only he could contrive a way of doing it. What the square law tells us is that there's a terrific advantage to be gained simply from having more units on the battlefield than the enemy, and that survivorship isn't to do with a simple subtraction, but with a subtraction of squares. It's just Pythagoras' theorem. When 2 forces comprise equally effective units, survivorship calculations can be represented on right-angled triangles. Here, for instance, red outnumbers blue by 17 units to 15. Red will win the battle, and it's a straightforward matter to calculate the survivors. The square root of 64, which is 8. Blue Commander knows that if he's going to get anywhere at all, he must try and get a numerical advantage. He can't add reinforcements to his own force, but can he do anything about reducing the size of the other side? If he can split the red force, he might get somewhere, even if it means having to fight 2 battles, one after the other. Here's the first battle. Blue won it, and he's still got surviving units available for the second battle he's left himself to fight. But are there enough units left? Yes, and he's even got a few left at the end of the second battle. The trick of splitting the opposing force does appear to have worked. The difficulty, of course, lies in getting Red Commander to allow his forces to be split. He'll know the principle of concentration as well as anybody. The thing to do is not to give him a choice. And this is how Nelson described his strategy in a memorandum written just before the battle. I have therefore made up my mind to keep the fleet in that position of sailing, with the exception of the first and second in command, that the order of sailing is to be the order of battle, placing the fleet in 2 lines of 16 ships with an advance squadron of 8 of the fastest sailing 2-decked ships. Nelson's tactical scheme went essentially like this. While he couldn't contrive the situation of 2 consecutive battles while keeping his own fleet together, he planned to use 8 of his warships to split the enemy fleet down the middle. This leaves 32 ships to engage 23, a superiority in fighting strength of almost 2 to 1. Even allowing for the total loss of the 8 without inflicting damage, this would still enable him to engage the other half on equal terms. And in fact, the 8 ships would almost certainly cause some damage to the enemy fleet. To put it another way, the square law indicates a British survivorship at the end of the battle of something between 5 and 6 ships. Not many, but much better than the crippling defeat forecast when keeping the fleets intact. Incidentally, let's take a look at what might have been the conclusion of the battle if Nelson had split his fleet not into 32 and 8, but into 31 and 9, which he might easily have done, using a small fleet of size 9 rather than 8 to split the enemy fleet. The 31 still win over 23, and 9 still lose, but the survivors from each engagement are different. In fact, different enough for the French fleet to be the stronger. The square law forecasts a French win at the end, with exactly 4 ships surviving. In fact, the actual force sizes on the day were different, 27 to 33, a situation slightly worse than that assumed in the memorandum. Events took place according to a slightly different scheme, but the idea of concentration followed the original. Lanchester wrote, "Nelson, if not actually acquainted with the square law, must have had some equivalent basis on which to figure his tactical values." And we all know what happened. The square law isn't of universal application to conflict. For instance, it wouldn't apply to conflicts where a single shot could cause multiple casualties, or to a battle which didn't involve precise targeting, such as a gas attack. But it is a memorable principle to have been developed from the simple deterministic model. But let's not forget the random model. There's something else one should try to remember. The military theorist von Clausewitz wrote this: "War is the realm of chance. No other human activity gives it greater scope. No other has such incessant and varied dealings with this intruder. Chance makes everything more uncertain and interferes with the whole course of events."